Hello. Welcome to the first of the Variational Inference series. My name is Chieh from Northeastern University, and I thought I will go over very quickly, well, as much quickly as I can, how variational inference work. I've had personally a lot of trouble with the variational inference when I was learning it, and I think the biggest reason is because variational inference just requires a lot of background information to be absorbed before you even understand it. So I'm going to be dividing these series into various sections so that you can absorb a concept one at a time. So the first today we'll go over some basic stuff. You need to understand things such as information theory, at least the basics of information theory. Concepts such as information, entropy, information, entropy, and differential entropy. Now, if you already have a good idea of what they are, you can, for the most part, just skip them and concentrate on the other portions. But I will start by giving a good understanding of these like prerequisites. After information theory, I think I will go over some stuff with KL divergence, its derivation, as well as how KL divergence is related to log of probability of x and KL divergence. After that, I think I'll do a little motivation lecture on graphical models. Graphical models, which we will talk about how it's very easy to get the joint distribution. However, it is difficult. This is easy to get. It's difficult to get the conditional. So this is difficult. And for this reason, variational inference is very useful. After that, I think I'll start talking about variational inference finally. Variational inference. And we'll probably, if we have the chance, do some examples so that you know how to use the variational inference. So, without further ado, I think the first thing we should do is the information theory portion. So, information theory, how do you quantify and measure information? Well, let's say that we're talking about some I just let's say you're in a class and you just learn about Civil War. Yeah. Civil War. And you may remember Civil War was between the North versus the South. So somebody tells you, given that you didn't already know, that the North won. Well, how much information was that? Well, according to information theory, information follows this equation: minus log probability of the event. So X right here is the event, right? And probability that the event is equal to that the North won versus the probability the event that the South has won. And let's say this is equal to 50-50, 1/2 and 1/2. So according to this equation here, we would say that, well, somebody just told you that the North has won. So this is the event. And therefore, I is equal to minus log of 1/2. Now, if you remember your calculus class, this is equal to 1. So this is 1 bit of information, assuming if we used the base of 2. This right here is called the base. And this tells you how you're going to represent the information. So you can represent information in terms of ones and zeros. That will be base 2, which is what we just used. Or very often we like to use base 10, which means the numbers are between 0 to 9. So we'll see numbers like this. So these are numbers based between 0 to 9. So depending on how you want to represent information in which base, you will pick this value. And since 2 is very convenient in engineering, for this case, we just pick 2. In other cases, you might pick 10 or even exponential, e. So yeah, this is how you calculate information. Information equation right here. This one here. So now, of course, they are not always, information is not always an integer. This right here could have been something like, could have been something like 3/4, so that the probability that North will win is much higher than the probability that the South will win. So in this case, we'll do it again, minus log of 3/4. Now, in this case, you're going to need a calculator. And if you were to, pull out a calculator, you will get, I think, 1.212, something like that. Now, notice this information is 0.12 is less than 1, which is what we got before, assuming base 2. This is what we got before. So, well, this one is a larger probability. 3/4 is larger than 1/2, right? And now you're getting a smaller information. This brings us to the very first property, well, a very important property of information, property, which is the higher the probability, the lower the amount of information. And this makes a lot of sense. Like think about if I had told, let's say the event, okay? Event could either be event could either be snow in Miami in July versus no snow in Miami in July. So if I tell you that there is no snow in Miami, which the probability is very high in July, you would probably say, yeah, I know that already. In Miami, it never snows in July. So I didn't tell you anything. So this bit of information didn't give you basically zero information. But this one, snow in Miami in July, is very unlikely. So if I tell you that, well, it snowed in Miami in July, you will probably be like, oh, wow, it snowed. Like it actually means something. So the amount of information, I'm actually giving you some information if I tell you that it snowed in Miami in July. So this property, where the higher the probability, the lower of the information, is very interesting. So let's say we look at a 2, let's say, a binary situation, whether it's a yes or a no. That it snowed or it didn't snow. Oh, actually, no. Let me get to that in a bit. The next concept I want to go over is actually more important. So we just talked about information, right? We found the information. We found the equation for it. Now, the next concept I want to introduce is called average information. Well, as you may guess, you average the information together. So it's very simple. But first, let's go over average, just in case everybody's on the same page. So let's say we have four numbers, and they're equally likely. So 1, 2, 3, 4. So 1/4. So they're equally likely. Equally likely. Okay, this is very important. I keep repeating equally likely. So now if we want to find an average in an equally likely situation, you would be 1 plus 2 plus 3 plus 4 divided by 4. Another way to write this is like this. 1/4 times 1 plus 1/4 times 2 plus 1/4 times 3 and 1/4 times 4. And this is a different interpretation. Is we have each number here. Number, 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 number. And right here we have the weight. Weight, weight. So if they're equally likely, then they have the same weight. And therefore this equation makes sense. The average equation. But what if this one is actually more likely? You will see 1 a lot more often than 2, 3, 4. Then when you start averaging them together, then it doesn't make as much sense. Let's say over here, instead of 1/4, this is 2/4. And these two are smaller. There's 1/8 and 1/8. Right here, 1/8. Okay. Now, if we want to find the average, the equation would then change. Average. Then we'll look at the first number. What's the weight? It's 2/8. Right? And then times 1. The second is 1/4 times 2. Then 1/8 times 3 plus 1/8 times 4. That's how you find the average. Very often people think of average in terms of this, but that's only because each number are equally likely. So this point needs to be drilled in. I'm sure most people knows this already, but I want to make sure everybody's on the same page. So now that's average. If we want to find average information, you just take the information of each one of them and average them together. Pretty simple. So let's look at the first one. Like, let's use this situation. The first one, the information again, is minus log of the probability, 2/8. So that's the first one. And the second one is minus log of 1/4. And the third one is minus log of 1/8. And the last one is minus log of 1/8. So if they have the same weight, you can just add them up and divide by 4. But they are different, so we need to multiply the weight in front of them. So it's 2/8 plus 1/4 plus 1/8 plus 1/8. So now this right here will give you the average information. Now, oh wait, there's another name. Oh yeah, average information is also known as entropy. Yeah, Now here's entropy. And therefore, what we can do, entropy normally is denoted with H. H is equal to this thing here. So we have 4 events, right? 1, 2, 3, 4. So probability of x1, as we see, is 2/8, and then probability of x2 is 1/4, and so on and so forth. So this same thing, right, could be rewritten as such. H is equal to probability of x1 minus log of probability of x1, and then minus probability of x2, log of probability of x2, and so on and so forth for the last 2 over here. And this summation can then be organized like such. Summation I from 1 to 4, probability of xi, log probability of xi. So that will equal to h. Of course, very often we don't only have 4. We might have 5, 6, all the way to like n, right? So instead of, for a general equation, you will most likely see this. H is equal to I equal to 1 to n, probability of xi, log probability of xi. And this right here is called entropy, also known as average information. So we have gone through now the idea of information right here, information. And then we average the information together, which for every single event, then that turns into this thing called entropy. So that's what we have. The next concept then I want to introduce after you understand entropy is, well, this right here is in the discrete domain. So the numbers are integers. Well, what if the numbers are real? So they're in the continuous domain. It's actually very simple. If this right here, if it's in the continuous domain, is called differential entropy. Okay, differential. And all you have to do is change the summation into integration. Minus integral right? Now, this is also then allows you to calculate with things with probability density function instead of probability mass function. So this is PMF. These ones are PDF. Probability density function. So let's do a very quick example of how to do this. Let's say we have probability of x. We'll do exponential distribution. This is a good one. Right, so this is exponential distribution. Now, if we want to find the entropy, differential entropy, it will be like this. Minus lambda e to the minus lambda x, right? So this, I copied it. And then log lambda e to the minus lambda x dx. Okay. Now, we can copy this part. Oh yeah, and the range, it goes through the entire range from 0 to infinity. That's what exponential distribution. X belongs to 0 to infinity. Now, we can reorganize this. Lambda e to the minus lambda x log of lambda plus, actually no, minus lambda x. So this lambda gets distributed into this dx. Okay, and then you can distribute this further at 0 to infinity. Lambda e to the minus lambda x log of lambda minus lambda x lambda again e to the minus lambda x dx. Now I'm going to rewrite this again. 0 to infinity lambda minus lambda x. No, wait 1 second. Minus log of lambda integral lambda e to the minus lambda x dx plus lambda integral x lambda e to the minus lambda x dx. Okay, now this is, in this form, things are simple. Because this right here is just the original function. This is the original p of x dx minus log of lambda. And this right here is the definition of expectation. X, p of x, dx. So if you look it up, the expectation, this right here is expectation of x. So if you look it up, the expectation is actually 1 over lambda. And therefore, lambda divided by lambda. And over here, the integral of the entire probability distribution is always equal to 1. And therefore, we got minus log of lambda. From this, we just got minus h is equal to plus 1. And that's that. So the 3 concepts we went over today, one is information. How do you calculate information? Well, I is equal to minus log of some base probability of x. Now, then we have entropy, also known as average information, where h is equal to minus summation I from 1 to n probability of xi log some base probability of xi. And lastly, I show you what differential entropy is. Well, it's just changing it into integral. Okay, and that's it. In the next lecture, we're going to go over KL divergence. And that will really, really help you onto the next step. All right, thank you.